Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today, we are going to discuss about the module The Special Theory of Relativity 2 from the paper Electromagnetic Theory. So in this module, we will continue to study the special theory of relativity. From this module, the students will get to know about the following. 1. The light cone and the proper time of an event is a Lorentz invariant quantity. Secondly, we'll get to study the law of addition of velocities in relativity. That is, the relation between the velocities of a particle as viewed from two different frames of reference. Then we will also get to know the introduction of the four vectors, that is, we'll get to study the four vectors, the velocity and the energy momentum four vectors. Then we will also study the very celebrated Einstein's energy mass relation, and we will then study the mathematical description of the properties of space-time in special theory of relativity and the introduction of the four tensors. So in the last module, we had begun our study of the Einstein's special theory of relativity. We had described the experimental basis of the need for the special theory of relativity and introduced the two Einstein's basic postulates for special relativity. We had then derived the Lorentz transformations and briefly discussed some of its salient consequences like length contraction, time dilation, and the relativistic Doppler effect. Finally, we had briefly introduced the concept of four vectors. So in this module, we will continue with the theory of special relativity, discuss some further consequences of Lorentz transformations, and study in detail the space-time structure of special theory of relativity. So now let us look at the light cone and proper time concepts. So when we are looking at this, if we look at the figure that is drawn over here, then we see that in the figure, the time axis is vertical and the space axis are perpendicular to it. For simplicity, only the x-axis is considered. At time t equal to 0, a particle is at the origin. Because no particle or physical system can have speed greater than the speed of light, the space-time domain can be divided into three regions by a cone called the light cone, whose surface is specified by the equation x square plus y square plus z square minus c square times t square is equal to 0. So in the figure, of course, it appears as a pair of straight lines. Light signals emitted from the origin at t equal to 0 would travel along the light cones. Any material system has a speed less than the speed of light, that is less than c. Then as time progresses, it would trace out a path called its world line. This world line will lie inside the upper half cone, and at every instant the angle made by the tangent of the curve must be greater than 45 degrees. Since the path of the particle must lie in the upper half of the cone for t greater than 0, that region is called the future. Light cone and proper time. So just like we were discussing about the light cone and proper time, so basically if we look at this cone, so the lower half of the cone is called the past. The axis, so basically we've got two inverted cones which are joined together at the tip of the cone along the axis, which we called as time t equal to 0. So the normal cone refers to the future. The tip of this normal cone, which is coincident with the tip of the inverted cone, refers to the time t equal to 0, that is the present, and the inverted cone refers to the past, which is the lower cone, and the shaded region of the figure for which the equation x square plus y square plus z square is greater than c square times t square is called elsewhere. So what one is wanting to say is that there are now three regions that we have defined. The axis x square plus y square plus z square is equal to c square times t square defines the axis of these cones. The equation x square plus y square plus z square less than c square times t square defines the area within these cones, while this third equation, that is x square plus y square plus z square is greater than c square times t square, defines the area that is outside this cone and is called elsewhere. Now, a system which is at the origin at time t equal to 0 can never reach or come from a point in the elsewhere region. Further, we will now define the invariant time interval between two events. And so if we consider the two events having the coordinates t1 and the vector x1 and the coordinates t2 and the vector x2, then the invariant interval between these two events is defined as s subscript 1 2 whole square is equal to c square times bracket open t1 minus t2 bracket close whole square minus modulus square of the modulus of the vector x1 minus vector x2, or we can then further write this as ds square is equal to c square times dt square minus d vector x square. This ds square quantity is invariant interval between the two events. Now let us look at the coordinates for the same events in another frame of reference, which is again inertial and which is moving with respect to this frame of reference with a speed v along the x-axis. And then the coordinates for the same events in this new frame of reference are t1 prime and vector x1 prime and t2 prime and vector x2 prime. Then the invariant interval between these two events in the new frame of reference is s subscript 1 2 prime square, and since it's invariant in any transformation, therefore the quantity s subscript 1 2 prime square is equal to the quantity s subscript 1 2 square. Thus, for any two events, there are three possibilities that we can define from these equations and the invariant interval that we have defined. First of the three possibilities is s subscript 1 2 square is greater than 0. This invariant interval is called time-like separation, and we can always find a frame of reference by a Lorentz transformation in which the vector x1 prime is equal to the vector x2 prime, which define the two events. But we cannot find a frame of reference in which the two events are simultaneous. That is, we cannot find a frame of reference in which t1 prime is equal to t2 prime. This is something that we can see from the above equation in which we have defined s subscript 1 2 square, that if x1 vector is equal to x2 vector, then the quantity on the right hand side of the equation is positive. But if we put t1 prime equal to t2 prime, then the quantity on the right hand side of the equation becomes negative and hence does not satisfy this possibility. The second possibility is s subscript 1 2 square is less than 0, and this is referred to as the space-like separation. Now in this possibility, or in this case, it is always possible to find a frame of reference in which t1 prime is equal to t2 prime for the two events, that is, the simultaneity of the two events is possible. However, one cannot find two coordinates in a frame of reference such that x1 prime is equal to x2 prime, which define the coordinates for the two events. And this again we can see from the same equation that we referred to earlier, that if we put t1 prime equal to t2 prime, we will get the quantity on the right hand side which is negative or less than 0, which satisfies this possibility or this condition. While if we put x1 prime equal to x2 prime, then the equation on the right hand side is positive or greater than 0 and hence violates this condition. Light cone and proper time. The third of the possibilities that we were discussing is that the s subscript 12 square is equal to 0, and this is referred to as the light-like separation. And for this case or for this condition, the two events that we were considering can be connected only by a light signal. That is, if one point lies at the origin, the other must lie on the light cone, that is on the axis which defined the light cone. Here what is important to note is that the division of the separation between the two events into the three categories that we have defined above is Lorentz invariant, and that the concept that we discussed regarding the past and the future are absolute concepts in terms of the light cone and proper time. Now let us discuss the concept of proper time. So let us consider a particle which is moving with the velocity vector u as a function of time t in some inertial frame of reference k. Now the square of the infinitesimal invariant interval ds is ds square is equal to c square times dt square minus d vector x square, and this can then be written as equal to c square times dt square times bracket open 1 minus beta square bracket close, where beta is equal to the modulus of the velocity vector u divided by the speed of light c. So in the frame of reference in which the particle is instantaneously at rest, or in the rest frame of reference, we can write down the quantity d vector x prime is equal to 0 and the quantity d t prime square is equal to, using Lorentz transformations, we get d t prime square is equal to dt square times bracket open 1 minus beta square bracket close, and this can then be written as dt square by gamma square as a function of time t. Follows that d tau, which is equivalent to dt prime, is equal to dt by gamma as a function of time t. From this we can rearrange the terms to write dt is equal to gamma as a function of tau times d tau. dt is given as t2 minus t1. So dt is equal to t2 minus t1, and this is equal to integral with limits from tau 1 to tau 2 over gamma as a function of time tau integrated over d tau. Here tau is referred to as the proper time of the particle, and we define this proper time of the particle as that time which is seen from the rest frame of reference or the time coordinate of an event measured in the frame of reference in which the event is at rest. Addition of velocities. So the way we have defined proper time and also using the concepts of the light cone, we can now talk about the addition of velocities. And this concept of addition of velocities basically expresses the phenomena of time dilation. So if we look at the time interval in the rest frame of reference, that is d tau, that same time interval appears as an interval gamma as a function of tau times d tau, which is greater than the time interval d tau in a moving frame of reference. Now, using these concepts, let us define or discuss the addition of velocities of a particle which is moving with a speed, let's say vector u prime, in the k prime frame of reference, where the k prime frame of reference itself is moving with a speed v in the positive x direction with respect to the frame of reference k. And as before, we must keep in mind that both these frames of reference are inertial frames of reference. So applying Lorentz transformation to the infinitesimal intervals, we can write down dx subscript 0 is equal to gamma times bracket open dx subscript 0 prime plus beta times dx subscript 1 prime bracket close. Here, if we can recollect from the 4 vector coordinate system that we had defined earlier, that x0 refers to the coordinate c times t, x1 refers to the coordinate x, x2 refers to the coordinate y, and x3 refers to the coordinate z. So dx subscript 1 is equal to gamma times bracket open dx subscript 1 prime plus beta times dx subscript 0 prime bracket close, and dx subscript 2 prime is equal to dx subscript 2 and dx subscript 3 prime is equal to dx subscript 3. Now, if the velocity of the particle in the k frame of reference is vector u, then we can write down using the addition of velocities that we had discussed earlier, u1 is equal to c times dx1 by dx0, and this is equal to u1 prime plus v upon 1 plus u1 prime times v by c square. u2 is equal to c times dx2 by dx0, and this is equal to u2 prime by gamma times bracket open 1 plus u1 prime times v by c square, and u3 is equal to u3 prime by gamma times bracket open 1 plus u1 prime times v by c square bracket close. So in this manner, we define the 3 components of the velocity of the particle in the k frame of reference. And from the above equations, one can see that the parallel components transform differently from the transverse components. So in the above case, u1 is the parallel component, while u2 and u3 denote the transverse components. So if we denote the parallel component of the velocity with the symbol vector u parallel, then this is equal to vector u parallel prime plus vector v upon 1 plus dot product of vector v times vector u prime by c square. Vector u perpendicular is equal to vector u prime perpendicular upon gamma times bracket open 1 plus dot product of vector v with vector u prime by c square. And for the simple case of all velocities in the x direction, we have the velocity u is equal to u prime plus v within brackets upon bracket open 1 plus v times u prime by c square whole bracket close. Velocity and energy momentum for vectors. Now, just like we had defined the position 4 vector or the coordinate 4 vectors, which included the 3 position coordinates and 1 time coordinate, similarly we can define the velocity 4 vectors and the energy momentum 4 vectors. So let's first start with the velocity 4 vectors. As for the discussion that we were doing just now, where for normal velocities, that is the velocities that we encounter in our daily lives, we know that the velocity u prime, that is the velocity with which the event is or the object is moving in the k prime frame of reference, and the speed v with which the frame of reference K prime is moving with respect to the frame of reference K, we can then write down that u prime and v are both much less than the velocity of light c. For this case where u prime and v is much less than the velocity of light c, we can define the normal transformation of the velocity as u is equal to u prime plus v, which is the well-known result for Galilean relativity. Here either u prime or v or both equal to c implies that u is equal to c, and c is indeed the upper limit on material speeds. That is, we cannot have a material which can move with a speed greater than the speed of light. And the other important result that we get is that the speed of light in all inertial frames of reference is the same. Now let us look at the velocity and the energy momentum 4 vectors. So supposing we define the position 4 vector as x superscript mu and the invariant quantity d tau, which is the time interval in the rest frame of reference, and this is not equivalent to the quantity dt because that is not invariant. So using these two relations, we get the velocity 4 vector as u superscript mu is equal to dx superscript mu by d tau, that is the derivation of the position coordinate x superscript mu with respect to the proper time tau. So if we look at the different components of this velocity 4 vector, we have u superscript 0 is equal to dx superscript 0 by dt times dt by d tau. So what we've done is that we have multiplied and divided the equation with respect to dt, and using this we get the result that u superscript 0 is equal to gamma times c, where dt by d tau is equal to gamma and dx naught by dt is equal to c, because x naught is given by c times t. So the derivation of c times t with respect to time gives us the speed of light c. Now the velocity vector u is given by the differentiation of the position vector x with respect to the proper time tau, that is dx vector by d tau, and this can then be written as dx vector by dt times dt by d tau, and this is equal to gamma times the velocity vector u. So if from this definition of the velocity 4 vector, if the mass of the particle being considered is m, then we can consider another 4 vector denoted by the symbol capital P superscript mu, and this capital P superscript mu is equal to m times capital U superscript mu, where m is the mass of the particle and capital U superscript mu is the velocity 4 vector of the particle. So again, from the different components that we can get from this equation, that is taking mu equal to 0, 1, 2 and 3 for the 4 different components, we get the result that the momentum vector p vector is equal to m times the velocity vector u, and this is equal to m times gamma times the velocity vector small u, where the velocity vector small u is the velocity of the particle, and the 0th component of this 4 vector p superscript mu, that is p subscript 0, is equal to m times capital U subscript 0, and this is equal to m times gamma times the speed of light c. So the vector capital P is like the non-relativistic momentum, except that the mass is multiplied by the factor gamma. Here the mass m refers to the rest mass of the particle, and m times gamma is equal to m upon under root 1 minus u square by c square is the effective mass of the particle when moving with a speed u, small u. And we see that in comparison to the rest mass of the particle, that is the mass of the particle when measured in a frame of reference in which the particle is at rest, the mass of the particle when measured in a frame of reference in which the particle is moving with a speed u, small u, the mass increases by a factor gamma. The ordinary or the rest mass is normally written as m naught, and the mass as measured in a frame of reference which is in which the particle is moving, that is the mass as a function of the speed v, is written as m naught times gamma. Further, if the speed v tends to the speed of light c, then the mass of the particle as measured in a moving frame of reference, m as a function of v, tends to infinity. Therefore, no material particle can move with the speed of light. Einstein's mass-energy relation. Now, once we have defined this energy momentum 4 vector, it is interesting to see that what is the zeroth component of this energy momentum 4 vector, that is capital P subscript 0. So if we look at this component of this energy momentum 4 vector and multiply this component with the speed of light c, then what we get is c times capital P subscript mu, where mu is equal to 0, or c times capital P subscript 0 is equal to gamma times m times c square. Now if we expand in the powers of v square by c square, then the above equation, that is c times capital P superscript 0, which is equal to gamma times m times c square, can be written as m times c square bracket open 1 plus half times v square by c square plus higher orders of v square by c square bracket close. Here we get this term when we consider gamma as equal to 1 upon under root 1 minus v square by c square. So we can write this as the whole term, that is gamma times m times c square, as m times c square times bracket open 1 minus v square by c square whole to the power minus half. And when we do an expansion of this as a Taylor series, then we get the above equation. Here the second term in the expansion, that is half v square by c square, is just the usual kinetic energy term. So when we open the bracket, the total terms that you get is c times capital P superscript 0 is equal to mc square plus half mv square plus higher order terms. So the second term in this expansion is just the usual kinetic energy term. The first term is a constant present even when the velocity of the particle is 0, that is when the particle is at rest, and is referred to as the rest energy of the particle. And this led Einstein to make a very bold suggestion that a particle of mass m, that is the rest mass m, has the energy E, which is equal to m times c square by under root 1 minus v square by c square. And this is exactly the term that we were discussing above, which was c times capital P superscript 0. So in other words, this c times capital P superscript 0 denotes the total energy of the system, where m times c square is the rest energy of the system and half mv square is the kinetic energy of the system. And this total energy E is equal to m times c square by under root 1 minus v square by c square is the total energy of whether the particle is at rest or in motion. While if the particle is at rest, then the energy E is equal to mc square, and this is called the rest energy of the particle. So the above equation is basically the very, very celebrated Einstein's energy mass equivalence relation, and it says that mass and energy are equivalent and interchangeable. Mathematical properties of space-time. We now develop the properties of space-time manifold in the special relativity in a consistent manner. Three-dimensional rotations in mechanics can be discussed in terms of group of transformations of coordinates that leave the norm of the vector invariant. In special relativity, the relationship between coordinates in different inertial frames are provided by Lorentz transformations that leave invariant the interval defined by s square is equal to x naught square minus x1 square minus x2 square minus x3 square. The group of transformations that leave the interval invariant is called the homogeneous Lorentz group. This includes the Lorentz transformations and also include the ordinary rotations. From the first of the Einstein's postulates, law of nature must be the same in all inertial frames of reference. They must be invariant in form under Lorentz transformations or be covariant. Every term of an equation must transform in the same manner under Lorentz transformations. Such equations must be expressed by relations among four scalars, four vectors, etc., defined by their transformation properties under Lorentz transformations. In the invariant interval, one of the terms appears with opposite sign. This makes the space non-Euclidean with accompanying complications. Four vectors and tensors. Up till now, we have discussed three different types of four vectors. First was the coordinate four vector or the position four vector. Next was the velocity four vector, and then we discussed the energy momentum four vector. Now, let us for the moment not restrict ourselves to Lorentz transformations and write the invertible transformation law from unprimed to primed coordinates as x prime superscript alpha is equal to x prime superscript alpha, where this is a function of the coordinates x superscript 0, x superscript 1, x superscript 2 and x superscript 3, and the alpha takes the value 0, 1, 2 and 3. Similarly, the inverse transformation can be defined as x superscript alpha is equal to x superscript alpha as a function of x prime superscript 0, x prime superscript 1, x prime superscript 2 and x prime superscript 3, where alpha again takes the value 0, 1, 2 and 3. A Lorentz scalar or a tensor of rank 0 is a single quantity whose value is not changed by the transformation. So when we are taking the 0th component of this four vectors, then it is a Lorentz scalar and is referred to as a tensor of rank 0. So invariant interval that we had defined earlier is one such quantity, and so are the charge and the rest mass of the particle. That is, when we consider the charge of a particle or the rest mass of a particle, they are also invariant quantities or tensors of rank 0. A contravariant vector or tensor of rank 1, that is A superscript alpha, is a set of four quantities or four vector which transform according to the rule when we are going from one coordinate system to the other coordinate system as A prime superscript alpha is equal to partial derivative of x prime superscript alpha with respect to x superscript beta, that is del x prime alpha upon del x beta whole times A superscript beta. So expanding this, we can write down A prime superscript alpha as equal to, taking alpha values from 0, 1, 2 and 3 and expanding this in terms of beta, which again takes the value 0, 1, 2 and 3. So we can write A prime alpha as equal to partial derivative of x prime superscript alpha with respect to x superscript 0 whole times A superscript 0 plus partial derivative of x prime superscript alpha with respect to x superscript 1 whole times A superscript 1 plus partial derivative of x prime alpha with respect to x superscript 2 whole times A superscript 2 plus partial derivative of x prime superscript alpha with respect to x superscript 3 whole times A superscript 3. Similarly, a covariant vector or tensor of rank 1 is a set of 4 quantities denoted by the term A subscript alpha, or in order to avoid confusion, B subscript alpha, and transforms according to the rule B prime subscript alpha is equal to partial derivative of x superscript beta with respect to x prime superscript alpha whole times B subscript beta. Now, if we expand this relation in terms of beta taking the value from 0, 1, 2 and 3, and alpha also takes the value 0, 1, 2 and 3, then we can write B prime subscript alpha is equal to partial derivative of x superscript 0 with respect to x prime superscript alpha whole times B subscript 0 plus partial derivative of x superscript 1 with respect to x prime superscript alpha whole times B subscript 1 plus partial derivative of x superscript 2 with respect to x prime superscript alpha whole times B subscript 2 plus partial derivative of x superscript 3 with respect to x prime superscript alpha whole times B subscript 3. 4 vectors and tensors. Now let us define the 4 tensors of rank 2, and there are 3 different kinds of 4 tensors of rank 2 that can be defined. So first of these 3 kinds of 4 tensors of rank 2 is the contravariant tensor of rank 2, which is denoted by f superscript alpha beta, and this is a set of 16 quantities that transform according to the transformation rules given by f prime superscript alpha beta is equal to partial derivative of x prime superscript alpha with respect to x superscript gamma whole times partial derivative of x prime superscript beta with respect to x superscript delta whole times f superscript gamma delta. The other 4 tensor of rank 2 that can be defined is the covariant tensor of rank 2 given by g subscript alpha beta, which transforms as g prime subscript alpha beta is equal to partial derivative of x superscript gamma with respect to x prime superscript alpha whole times partial derivative of x superscript delta with respect to x prime superscript beta whole times g subscript gamma delta. And the third of the 4 tensors of rank 2 is called the mixed tensor of rank 2 and is denoted by h prime superscript alpha subscript beta and transforms according to the transformation rule given by h prime superscript alpha subscript beta is equal to partial derivative of x prime superscript alpha with respect to x superscript gamma whole times partial derivative of x superscript delta with respect to x prime subscript beta whole times h superscript gamma subscript delta. Using these kind of transformations, we can generalize the above definition to higher rank tensors also. Now let us define the inner or the scalar product between 2 tensors, and this is defined as the product between a contravariant and a covariant vector. So if A is a contravariant vector and B is a covariant vector, then their scalar or dot product or inner product is defined as A scalar product with B is equal to A superscript alpha B subscript alpha. And if we expand this, then using the transformation equations, we can write down the same scalar product or the inner product for in a different frame of reference as A prime dot B prime is equal to A prime superscript alpha B prime subscript alpha, and using the transformation equations defined above, we can further write this as equal to partial derivative of x prime superscript alpha with respect to x superscript beta whole times partial derivative of x superscript gamma with respect to x prime superscript alpha whole times A superscript beta B superscript subscript gamma and this is equal to partial derivative of x superscript gamma with respect to x superscript beta whole times a superscript beta b subscript gamma, and this is equal to the delta function superscript gamma subscript beta whole times a superscript beta times b subscript gamma, and this is equal to a superscript beta times b subscript beta and is equal to a dot b. So in this manner we see that the inner or the scalar product is invariant under a transformation from one frame of reference to the other frame of reference. The metric tensor. The metric tensor of special relativity. Now in the differential form, the invariant interval that defines the norm in our space is given by ds prime square is equivalent to ds square, and this is equivalent to dx superscript 0 square minus dx superscript 1 square minus dx superscript 2 square minus dx superscript 3 square. So if we write the norm or the metric as ds square and define that in terms of the tensor notation, then we can write this as ds square is equivalent to g subscript alpha beta whole times dx superscript alpha times dx superscript beta. Then this quantity g subscript alpha beta, that is the second rank covariant tensor g subscript alpha beta, has the components, if we compare this equation of the interval ds square with the above equation of the interval, we have that g subscript 0 0 is equal to 1, g subscript 1 1 is equal to g subscript 2 2 is equal to g subscript 3 3 is equal to minus 1. Further, this second order covariant tensor g subscript alpha beta is defined or is called the metric tensor and is diagonal, that is all its off diagonal elements are equal to 0. The corresponding contravariant metric tensor is defined by g superscript alpha beta is equal to g subscript alpha beta numerically. So g subscript alpha beta is equal to g superscript alpha beta is equal to the matrix whose first row has the components 1 0 0 0, second row has the components 0 minus 1 0 0, third row has the components 0 0 minus 1 0, and the fourth row has the components 0 0 0 minus 1. In other words, g superscript alpha beta and g subscript alpha beta are numerically equal and form a 4 by 4 matrix whose off diagonal or non-diagonal elements are all 0. That means it's a diagonal matrix, and the diagonal elements are defined as per the matrix given over here. Further, if we take the product of these two metric tensors, that is g subscript alpha gamma whole times g superscript gamma beta, then this is equal to delta alpha beta, that is a delta function having superscript beta and subscript alpha. Further, the invariant interval from this entire discussion can then be written as x superscript alpha times g subscript alpha beta times x superscript beta is equal to ds square. Playing with indices, raising and lowering of indices. The metric tensors can be used for the operation of lowering and raising of indices of a given tensorial quantity. So let us consider the example of a contravariant vector given by a superscript alpha. So we can define a corresponding covariant vector given by a subscript alpha by using the transformation A subscript alpha is equal to G subscript alpha beta whole times A superscript beta. So here the metric tensor G subscript alpha beta does the transformation of lowering the contravariant vector to the covariant vector. So expanding this in terms of beta taking the value 0, 1, 2 and 3 and alpha taking the value 0, 1, 2 and 3, we get A subscript 0 is equal to A superscript 0 from the definition of the metric tensor. A subscript 1 is equal to minus of A superscript 1. A subscript 2 is equal to minus of A superscript 2 and A subscript 3 is equal to minus of A superscript 3. So from this one can see that for every natural contravariant 4 vector, we also have a covariant 4 vector associated with it, and the covariant 4 vector can be obtained by the transformation that is discussed above. And from the above equation one can also conclude that while the time components of the contravariant and the covariant vector are the same, the space components of the contravariant and the covariant vector are equal in magnitude but opposite in sign. Here it is also important to note that in some of the textbooks, the way these metric tensor is defined is such that when you convert from the contravariant to the covariant or from the covariant to the contravariant vector, then the time component is equal in magnitude but opposite in sign, while the space components come out to be equal. But that depends upon how these quantities are being defined. So it is important to understand that both those formulations are correct depending upon how you're defining your metric tensor. Now, writing the general equation of a contravariant vector, we have x superscript mu is equal to x superscript 0 and the vector x. Then its corresponding covariant counterpartner is given by x subscript mu is equal to x superscript 0 and minus of x vector. The next thing that we need to understand is the contraction of indices. This normally we encounter when we are taking the dot product of two vectors. So basically the dot product or the inner product of two vectors is nothing but the product of the contravariant vector of the first quantity and the covariant term of the second quantity. So the dot product or the scalar product or the inner product of the two vectors A dot B can be written as A superscript alpha times B subscript alpha, and then this can further be written as, using the transformation using metric tensor, as G superscript alpha beta whole times A subscript beta times B subscript alpha, and this is equal to G subscript alpha beta whole times A superscript alpha times B superscript beta, and this is equal to B superscript 0 times A superscript 0 minus vector A dot vector B. So one sees that the contraction can be applied to any two indices, one of which is the contravariant term and the other is the covariant term. So for example, if we consider a rank 2 contravariant tensor T superscript alpha beta, then we can write down a rank 2 mixed tensor as T superscript alpha subscript alpha as equal to G subscript alpha beta times G subscript alpha gamma whole times T superscript beta gamma. Here it is important to note that whenever two indices are contracted, the rank of a tensor is reduced by 2. And when we are saying that two indices are contracted, that means that whenever we repeat two indices. the differential operator. Now, after having studied the metric tensor and the transformation of the contravariant and the covariant terms, we next come on to defining our different operators in the tensorial notation. So one of the first operator that we define in the tensorial notation is the differential operator. So let us consider the partial derivative of the operator with respect to the contravariant vector x superscript alpha and the covariant vector x subscript alpha. So the differential operator defined with in terms of the contravariant vector x superscript alpha is written as del by del x prime superscript alpha is equal to del x superscript beta by del x prime superscript alpha whole times del by del x superscript beta, and expanding beta in terms of 0, 1, 2 and 3, we can write this as equal to del x superscript 0 by del x prime superscript alpha whole times del by del x superscript 0 plus del x superscript 1 by del x prime superscript alpha whole times del by del x superscript 1 plus del x superscript 2 by del x prime superscript alpha whole times del by del x superscript 2 plus del x superscript 3 by del x prime superscript alpha whole times del by del x superscript 3, where alpha takes the values from 0, 1, 2 and 3. Now comparing this with the earlier equation shows that the differential operator with respect to the contravariant position vector behaves like a covariant vector. Here x prime superscript alpha is contravariant, while the differential operator defined as del by del x prime superscript alpha is a covariant operator. Similarly, differentiation with respect to a covariant component gives a contravariant operator, and this can be seen as, so let us define the del operator or the differential operator with respect to the contravariant component given by del by del x superscript gamma is equal to del x subscript alpha by del x superscript gamma whole times del by del x subscript alpha, and this is equal to del by del x superscript gamma acting on within brackets g subscript alpha beta times x superscript beta bracket close times del by del x subscript alpha, and this is equal to g subscript alpha beta times del operator superscript beta subscript gamma times del by del x subscript alpha, and this is equal to g subscript alpha gamma whole times del by del x subscript alpha. So from this we can write that del by del x prime superscript alpha is equal to del x prime superscript alpha by del x superscript mu whole times del by del x subscript mu. So we can therefore use the notation del superscript alpha is equivalent to del by del x subscript alpha, and this is equal to del by del x superscript 0 and minus del operator vector, while so this is the contravariant del operator which is actually defined in terms of the covariant vector. Similarly, the covariant del operator del subscript alpha is equivalent to del by del x superscript alpha, and this is equal to del by del x superscript 0 and the del operator vector. Finally, we define the invariant for divergence and the Laplacian operator in terms of the tensorial notation as del superscript alpha acting on the covariant vector a subscript alpha, and this is equal to del subscript alpha acting on the contravariant vector a superscript alpha, and this is equal to del a superscript 0 by del x superscript 0 plus the divergence of the vector A. The Laplacian operator is defined as del superscript alpha del subscript alpha is equal to del 2 by del x superscript 0 2 square minus del operator square. Matrix representation of Lorentz transformations. Now let us look at the matrix representation of Lorentz transformations. After we have defined the differential operator, we are now ready to define the matrix representation of the Lorentz transformation. So going back to the Lorentz transformation, we have x prime is equal to gamma times bracket open x minus vt bracket close, t prime is equal to gamma times bracket open v by c square times x plus t, that is gamma times bracket open minus v by c square x plus t bracket close, y prime is equal to y and z prime is equal to z. In the tensorial notation, we can write these Lorentz transformations as x prime superscript 0 is equal to gamma times bracket open x superscript 0 minus beta times x superscript 1 bracket close, x prime superscript 1 is equal to gamma times bracket open minus beta x superscript 0 plus x superscript 1 bracket close, x prime superscript 2 is equal to x superscript 2 and x prime superscript 3 is equal to x superscript 3. Or we can combine all of these equations in the tensorial notation as x prime superscript mu is equal to delta superscript mu subscript nu whole times x superscript nu, where delta superscript mu subscript nu is called the Lorentz transformation matrix. It's a mixed rank 2 tensor and is given by a 4 cross 4 matrix whose first row components are gamma minus beta times gamma 0 0. Second row components are minus beta times gamma gamma 0 0. Third row components are 0 0 1 0 and the fourth row components are 0 0 0 1. The inverse transformation for the Lorentz transformations or the inverse Lorentz transformations can then be represented as x superscript mu is equal to lambda inverse superscript mu subscript nu x superscript nu, where the inverse Lorentz transformation matrix lambda inverse is given by a 4 cross 4 matrix whose first row is gamma beta times gamma 0 0. Second row is beta times gamma gamma 0 0. Third row is 0 0 1 0 and fourth row is 0 0 0 1. So students, now let us summarize what we have learned in this module. So in this module, firstly, we studied about the special theory of relativity and we continued our discussion regarding the same. And while discussing this, we discussed an important concept which is called as the light cone and also defined the proper time of an event. So the proper time of the event is a Lorentz invariant quantity, that is something that we saw, and unlike the usual time, which is different in the different frames of reference. Then we also learned about the law of addition of velocities, that is the relation between the velocities of a particle as viewed from two different frames of reference, and we saw that these are different from the laws of addition of velocities under Galilean transformations, and we realized that these can be derived when we use the Lorentz transformations. The law of addition that we get differ profoundly from the usual laws of addition of velocities, and the law clearly demonstrates that the velocity of light is the upper limit to the velocity achievable by any material particle. Then we discussed the concept of four vectors, and we introduced it to define the four velocity vector, the four energy momentum vector, and finally we discussed the celebrated Einstein's energy mass relation. After that, a mathematical description of the properties of space-time in special theory of relativity was given, and from that we led to two kinds of four vectors, that is the contravariant and the covariant form, because of the peculiar structure of the space-time in Einstein's special theory of relativity. The idea of four vectors was then extended to four tensors, much on the line of ordinary vectors but with some clear differences. Thank you.